So last time we talked about delamination wear, and I said that delamination wear is removal of material in thin flakes and platelets. This occurs due to high shear and some plastic deformation every contact cycle. So delamination wear can take place even in a lubricated joint. Friction coefficient normally less than 0.3, so even in the lower coefficient of friction case, delamination wear can take place. So basically it happens because of the contact stress. So here we have got compressive stress if there is some loading, okay, but as we go deeper there is shear stress, and actually at some stage there is a maximum shear stress. So at this point the shear stress is maximum, as you know, because of shear stress the plastic deformation will take place, and therefore some plastic deformation will take place, and this plastic deformation will take place every time the surface comes in contact. So for example, if you imagine an IC engine, for example cylinder and piston, so at every point, any point, given point, there will be repeated sliding, okay, and because of this repeated sliding the plastic deformation continue to happen, but at some point this the material at this point will be completely strain hardened and what is called as ductility will be reduced. So because of repeated plastic deformation, ductility will be reduced, and therefore there is a good chance that some cracks can nucleate. So crack will nucleate, and the crack will grow from like this. Other crack will also nucleate here, for example, and grow like this. So these cracks will meet together and form this kind of small flake, and this normally happens very close to the surface, and therefore the thickness of these flakes are only few microns. So very thin flakes of particles will come out as debris. So this is called delamination wear, and delamination wear takes place in all kinds of lubricated sliding. If the coefficient of friction goes greater than 0.3, then this delamination wear will change into some other modes of wear, and the wear will change from mild wear to severe wear. So normally delamination wear will take place at a lower coefficient of friction, and it takes place because of repeated sliding at any given point. So the second one is fatigue wear. Fatigue wear is also very much related to similar in mechanism to delamination wear, but here the stresses are much higher, and this happens in rolling contacts. So in the rolling contacts, again the same mechanism because of the contact pressure. So the shear stress will be higher, okay, and the distance of this is given as 0.48 A for a Poisson's ratio of 0.3. If the Poisson's ratio is 0.3, this depth of this maximum shear point is given as 0.48 A, where A is the contact radius. So if we look at this contact radius, it will look like a circle if we have a ball on a flat plate, flat surface, and this is A. So depending upon the contact radius, the depth of this maximum shear point will be decided by this 0.48 A, and the value of maximum shear stress is given as 0.31 P naught, where P naught is the mean pressure. So mean pressure because of the load that we are applying. So load divided by the contact area will be the mean pressure, and it is 0.31 P naught. So this is the maximum shear stress. So mechanisms are similar, but here in this case it is not the sliding but it is rolling. So if you imagine any surface and there is a ball here, and if we look at the stress profile in the contact zone, the normal stress is elliptical like this, and then there is a tangential stress which acts and goes into the tensile, and so this side is compressive and below is tensile. So the radial stress is in this direction. It goes from compressive to tensile. The normal stress is from very high value to 0 here, and this is the contact radius, and the shear stress in the z direction is like this. So this is all the profile of the main stresses that are acting at the contact point. In the ball on a flat plate it is circular, but in a roller, for example ball bearing, a ball rolling in a raceway, the contact is elliptical, but the stresses will have the similar nature. So that means if the ball is rolling like this, so at this point there will be a tensile stress, and there will be some compressive stress, okay, again tensile stress, and there will be some shearing occurring at the subsurface. So that means the surfaces here are exposed to tensile, compressive and shear. And shear stress, and this is repeating. So this is all about the fatigue. So because of this fatigue, the cracks will nucleate at this point somewhere where the maximum shear stress is, and then it will grow. So similar to the delamination process, but here it's not the sliding but rather rolling, and it can happen even in several millions of cycles. So for this kind of wear, fatigue wear, there is no such thing as limiting stress. That means if we reduce the stress, it will not fail by fatigue wear, but this will not happen. At whatever stress you are working, fatigue wear will always take place. And this gives you one example of the fatigue wear. So this is the small chunk of material has come out. This is also known as pitting. So the material has come out, which you can see here, and once the material comes out, that small particle will act as a third body, and it will accelerate the wear process. So this is about fatigue wear. Next is the what is known as chemical wear. So our bearings do not function in a always in an environment where there may not be any chemical around. So there can be many such chemical things, and especially the first comes to our mind is presence of water. Okay, even though water is not a chemical, but when it is present in a machine element, it can cause corrosion. So all kinds of tribological contacts are subjected to corrosion. So any tribological system you take will be subjected to corrosion. So therefore, in our solution, we have to always take care of the corrosion. So material removal facilitated by chemical reactions between the material and or the ambient environment or elements, compounds present in liquid or solid form. So this is also known as corrosive wear. So this is a very normal problem, and you will see that when we talk about lubricants, the lubricants are filled or mixed with some corrosion inhibitors for this purpose. These compounds will help to reduce the effect of corrosion in the case of ferrous materials. For other materials like non-ferrous materials and ceramics, the chemical wear will be less. And polymers also, but polymers are quite affected by moisture or water. So water is or moisture is not good for polymers. So in general, to reduce chemical wear, we have to ensure that corrosion does not take place. Okay, but there can be other kinds of chemical environment which are part of your system, part of the design system. For example, presence of H2. Presence of hydrogen is nowadays getting common for hydrogen energy related. Applications. So for example, if we are handling hydrogen, and let's say we are pressurizing hydrogen in a compressor, so here hydrogen will react with metal surface, or even hydrogen will diffuse inside the metal surface. So diffusion can also happen. So in either case, whether it is diffusing or reacting and making hydride, again this chemical environment is affecting. Okay. Other than that, there are some many industries like oil related industries, fertilizers, these kind of printing, these kind of industries are have lots of corrosive chemical environment in the liquid form, and they will also affect the bearings. So often the bearings will fail not because of its lubricant per se, but it fails because of the corrosion that takes place. Next one is fretting wear. Fretting wear takes place in a reciprocating sliding with a small amplitude and high frequency. So in some application, such kind of reciprocation can happen within a small amplitude. Okay. So this is moving only few tenths of micron. So within this kind of movement, it can be created because of vibration. So even vibration can create this kind of fretting action. So if this kind of motion happens, then what will happen is small wear particles will be formed. It can be in a very small debris particles, but these particles will accumulate here and they are not going to be removed, and because of the presence of these wear particles, some further wear will take place, which is like a polishing action. So this wear particle acts like a polishing paste, and it will polish the surface here. Polishing basically means removal of the material. Often these wear particles are oxides, and these oxides are hard and therefore very abrasive in nature. Hardness is very high, and therefore they are very abrasive in nature. So this is the sequence of event that will take place in fretting, and it's basically third body wear. And sometimes fretting wear can also happen in a adhesive wear, where these two materials are adhering to each other. Okay, so because of high adhesion also fretting can take place. So in both way, either by the wear particles or by the adhesive action, fretting wear can take place. So fretting wear can happens in flanges or couplings, okay, keywage. So these are the places where the movement is very small, and therefore fretting wear will take place. Fretting wear can also take place in screw and bolt heads. Screws can also be subjected to fretting, or bolt heads. So often this kind of fretting will lead to loosening of the joints. And as you know, if the joints are loosened, the vibration will be even more, and because of the vibration, more vibration and more fretting will take place. So it becomes even a very accelerated fretting action. In the case of ferrous material, the fretting, the wear debris looks reddish brown, and in the case of aluminium it may look blackish wear debris. Okay, so this is how it takes place. And again, for reducing fretting wear, we have to either use a low friction material here, a lubricating material here, or we have to ensure that there is no vibration or there is no small amplitude at high frequency motion here. So the joints should be very tightened with high stress, so that there is no reciprocating sliding motion going on. Okay, and in some cases you will have to use some low friction materials. Okay, so this is how we can reduce fretting wear. In some cases, fretting wear is also known as false brinelling. So for example, in some rolling contact, especially in rolling contacts, some minute slip can happen. Okay, and because of this slip, the fretting action will happen, and in this case it is also known as false brinelling. So we should know this term, because in industry people use this kind of terms to mean basically fretting wear. Next is erosive wear. So this is a kind of abrasive wear by solid particles, liquid flow or liquid droplets or slurry flow. Okay. So the main thing in erosive wear is when the particle hits. So particle may be like this and it hits the surface. Okay. Because of presence of high velocity air or liquid or in a slurry. It can also take place by liquid droplets. So even liquid droplets can also lead to erosive wear. So in some cases we can use erosive wear for beneficial purpose, like for example cleaning a metal surface. You can do a sand blasting. So sand blasting is used to clean the metal surface, but the process is same as erosive wear. So erosive wear can be modeled by an equation where epsilon is the loss of the mass of the surface in question, of the material which is wearing out, divided by the mass of the impinging particles. That means the particles that you are using for abrasive wear. So basically loss of mass of the material per unit the impinging particles, the mass of impinging particles. So this is given as epsilon, and epsilon can be modeled as some constant k multiplied by the velocity power n. So v is the abrasive particle velocity and n is an index for the target material. The target material is this one. So n is the index. So we can use this kind of model or equation to quantify erosive wear. So erosive wear depends a lot on this angle. At what angle it is hitting the surface. Okay. Theta can be very, very small, or theta can be very large, 90 degree. Okay. So it can vary from 0 to 90 degree. And let me try to delete some. Oh, it comes back. And here is theta. So this curve is for ductile metals. And this is for brittle solid. So that means at certain angle, so here is 0 and here is 90 degree. So at certain angle, the for example for ductile metal, the situation is worse. So that means this angle will decide the rate of abrasive wear. So as we go towards 90 degree, the abrasive wear will be reduced. Okay, whereas in the case of brittle solid, it starts somewhere here and all of a sudden it goes very, very high. Okay, so at lower angle, the abrasive wear is low, but if the theta is higher and close to 90 degree, the abrasive wear is maximum. So this is the way materials will behave under abrasive wear situation, and it all depends upon how the particle is impacting. So for example, for brittle solids, if the particle is impacting right like this at 90 degree, this is the worst situation. The abrasive wear will be very high. But if it was a ductile material, in this situation, the abrasive wear will be very low. For ductile material, the abrasive wear will be something here when it hits like this, less than 45 degree. So this is the way ductile materials and the brittle solids will behave. Another thing is the value of N is in the range of 2 to 2.5 for most of the solids. Okay. So we can use this equation to model abrasive wear, and also we can try to reduce the abrasive wear by using this information. So abrasive wear takes place in the case of for example dust particles hitting blades of a turbo machinery, or in fluid bed combustors where we use particles as a combustion material, and particles in general in steam, wet steam also can act as a abrasive particle. So these are the examples where the abrasive wear erosive wear takes place, and we need to design so that we can avoid erosive wear, and sometimes we can use a hard material, hard and tough material to deal with this kind of erosive wear situation. Next we will discuss about lubrication. Yeah.
Sir, in the case of delamination wear and fatigue wear, sir, we are talking about, sir, rolling surface, no? We are not talking about contacting surface. Wear take place in rolling surface only.
In the case of delamination wear, it can be sliding also.
Yes, region is sliding. I want to say, sir, we are talking about only one surfaces, one parts of body, not other part of, that means another body.
Sorry, can you say again?
Like, sir, for generating friction, we require two body surfaces.
Yes,
Sir, also
yes, yes.
sir, in case of wear only, we are want to say, that means we are telling about wear take place in only rolling surface, but the one part of the surface only.
No, it can actually it can take place in either of the two surfaces. So
we cannot say that harder surface material will not wear out and only soft material will wear out.
yeah, we cannot say that, because for example this is a roller bearing. For example, if this is the cylindrical roller and this is the substrate on which it is rolling, both materials can be very, very hard, but that doesn't matter, because even the hard material will have the stresses. So stress will be very high, and therefore there will be some um, shear stress here, maximum shear stress. So at the maximum shear stress, because of plastic deformation, and also crack will initiate. So crack will initiate here. So even hard material will be subjected to this crack initiation. So how? Yeah.
Sir, in both the cases you told the crack initiation takes place in contacting surface.
Yes. So contacting surface can be this as well as this. It can happen in this
Oh,
surface also. So either of these surface will be subjected to this delamination wear or fatigue wear. Fatigue wear is basically for the rolling element bearings, but delamination wear can happen in, for example, piston and cylinder also. Okay, so this is not rolling element, this is sliding element,
yes.
right? And how we can reduce it is by first having the two surfaces of very high yield strength or hardness, we can say yield strength should be high. Okay, and another important is toughness should be high. Toughness should be high. And another is you might have heard about clean steel. So the steel which is used for making this kind of rolling element bearings are called clean steels because they do not have any impurities or any small oxide. Okay, so these steels are treated with vacuum in a vacuum induction furnace. They are treated so that all these kind of oxides and any gaseous, mainly gaseous will be oxygen gas will be removed, so that this is a clean steel. Clean steel basically means no impurities there, because the impurities are the point where the stress will be concentrated, right? Stress concentration will take place. So stress concentration will lead to fracture. I mean crack initiation, then crack growth, and final fracture. So lubrication. And so now so far we have discussed about friction, we discussed about wear, different types of wear mechanisms, and how we can solve those wear problems. So wear is very pervasive in all engineering systems, so we must understand all the details about wear, okay, as well as friction. But we go into the lubrication part where we are trying to find a solution to friction and wear. So lubrication is a method of reducing friction and reducing wear by the application of liquid, gas or solid of suitable viscosity, chemistry, and also we can call it lubricity. So friction can be reduced by employing a lubricant at the sliding contacts, or we can also reduce friction by converting sliding friction into rolling friction, but that is another aspect of how to reduce friction. So what is important is the viscosity. So we need to have lubrication because for many machine elements the load and speed or velocity, these are all decided by the design parameters. Okay, we don't have much control. Even the environment also we don't have much control, because these are decided by the design requirements, and accordingly the material will be selected. So therefore the tribological system, where the contacts will take place, or sliding or rolling, basically sliding will take place, is subjected to all these kind of loads and velocity and environment. We don't have much control. We should also add temperature, thermal. So therefore we have to study the tribological system very carefully and provide a proper solution. So the very first solution we look for is the lubrication. As I said, viscosity plays a very important role. Um, we will study about how viscosity is related to the shear stress. So viscosity basically helps to separate the two surfaces. So let's say we have got two surfaces and there is liquid in between, but since we have to apply some load, this liquid can get squeezed out in under different situations. Let's say flat on flat or non-conformal. In this kind of situation also, if the load is applied, the liquid can get squeezed out. So it will not work. Even if you lubricate the surfaces, they will not work. So therefore, the viscosity will play a very important role, because under a dynamic situation, the viscosity will ensure that a thickness of the fluid film always remains at this contact point. And the main thing is that in lubrication, if the two solids come in contact, direct contact, then lubricant basically is not working. So there is a very strong action of viscosity, and we have to ensure by selecting lubricant of sufficient viscosity so that a fluid film can always be formed. Often a parameter is given, which is lambda. Film thickness parameter is given by h over sigma, where h is the mean film thickness and divided by composite standard deviation of the two surfaces. So this has to be so the mean film thickness has to be at least equal to this one or more, right? So if lambda is equal to 1, that means the roughness so the film thickness and the roughness are almost same, so that means you have hardly any space here. But if lambda is greater than 1, that means you have got roughness is smaller compared to the film thickness. So that means now you have got some liquid present. So the value of lambda is very important, and that's the reason why all the bearing surfaces with lubrication are smoothened. They are very smooth surfaces, so that we can have very thick fluid film here. So if lambda is less than 1, still friction will be reduced, but not much. But if lambda is greater than 1, friction will be in the range of 0.001 or in this kind of range. So this is a very good situation. But we should remember that it is not always the case, even with lubricants. So many properties of the lubricants are important: viscosity, lubricity, thermal stability, boundary lubrication property, anti-oxidation, and non-toxicity. So viscosity just now we have discussed, and we will discuss more about the viscosity, how viscosity plays an important role. Lubricity is a less defined term which basically includes many properties of the lubricant. It can include viscosity and boundary lubrication property, and they tend to be large molecules. Large molecules materials tend to have high lubricity. Large molecule. and that's why many of the polymeric materials are better with high lubricity. Okay. Thermal stability means the lubricant that we are using should not degrade because of thermal environment. So many of the lubricants will be used in high thermal, high temperature condition, and very good example is IC engine. They are used at in the range of 180 to somewhere around 180 degrees Celsius. But many of the bearings also, the temperature can go high. It can go up to 200 degrees Celsius or even more. So under this kind of thermal condition, the lubricant will degrade. So they will degrade by oxidation, and also by, for example, shearing, which is also known as chain scission. Basically, breakage of the molecules into smaller. So if the molecule is very long and it gets sheared here, so now we have got two small molecules, and obviously with two smaller molecules the viscosity will go down and its performance will go down. So over time, because of thermal action, the lubricant will degrade. So this is a big cost for companies, because you have to always keep changing the lubricant because it is degrading with time. And this is one reason why we cannot use vegetable oils or animal oils for high-end applications, for high stress application. As well as we have got other varieties, mineral oils and synthetic oils. So mineral oils are less in terms of thermal stability compared to synthetic oils. So synthetic oils are the best in terms of thermal stability. So this is how we have to think about lubricant selection for our tribological application. Boundary lubrication is a property of the lubricant by which it forms some layers. So for example, if these are the two solids and we have liquid here, so this liquid is not just working because of the viscosity, but this liquid also is very active and it forms some layer here. And these kind of reactions are very, very complex, even not very clear how this kind of reaction takes place. But people explain that under high pressure and some temperature, this reaction will take place. So the molecules which are in the liquid or lubricant will react with the solid surface here and form a layer just like a coating, a very low shear or soft low shearing. So this is known as boundary film, and this method is called boundary lubrication. So every lubricant will have these property, and this property can be enhanced if we add some additives. So lubricants that we use are not single component, they have lots of additives, and there are two types of additives. One is called anti-wear and extreme pressure additives, and another is called anti-friction. So these additives basically will improve the property of the lubricant, and there are some chemicals which are added. One is called ZDDP. I will show you later the full form of this one. This is basically zinc sulfate and phosphate. And another is called TCP. So these are the two additives for anti-wear, extreme pressure, and for anti-friction there are some other kinds of additives possible. So this boundary lubrication is very important. It acts in all lubricants. So this basically ensures that these two solids never touch each other. So even under extreme pressure or any kind of situation, let's say this surface comes very close to this, okay, but still this boundary film will separate them, so they will not touch each other and wear will be avoided. So this is extremely important. In all oils they have this one, anti-wear and extreme pressure. Now another thing is anti-oxidation. So as we were talking about thermal stability, so one of the mechanism of thermal degradation is oxidation. So if we add some anti-oxidation filler or additive, we can reduce the time which takes to fully oxidize a lubricant or fully degrade a lubricant. So in general this will improve the lubricant life. Okay. So other properties could be non-toxicity is important in some cases. For example, if you are using a food industry, in food industry you cannot use toxic lubricants. So for example, in agriculture, you are using many machineries, but if these machineries are always giving some toxic lubricants to the soil, so the soil will get toxicated, right? And the productivity of the soil will be reduced. So in agriculture or agricultural machines, we should not use this kind of lubricants. So we should use lubricant which doesn't have toxic materials. Some of the materials like zinc sulfate and phosphate, as well as anti-corrosion additives are very toxic in nature. In food industry again we cannot use, because if the food comes in contact with let's say if you have a roll mill. In a roll mill we roll let's say any kind of food material, okay, and if these kind of lubricants come into contact with the food material will get poisoned. So therefore we should be very aware of this. Along with that, there are other properties, for example biodegradable. So we prefer to use biodegradable lubricants, so that in the long run these lubricants will be degraded and there will be nothing left. Most of these lubricants are contaminants. They contaminate soil, water, and to some extent air too, because they burn and the gases will go in the air. So they are very huge pollutant for our environment. So other additives are anti-corrosion, or it is also called anti-rust or rust inhibitor. inhibitors. These rust inhibitors are very, very toxic materials. They can be arsenic or some other kinds of toxic material. In addition to this, we also have detergents inside and dispersants. So detergents and dispersants are basically added to make the oil or lubricant free of deposits or sludge. So for example, if sludge or deposits are formed on the surface, it will not be good for lubrication. So these detergents will ensure that these sludge don't form. Okay, the surface is always clean of these sludges or any kind of deposits forming. So for that purpose, detergent and dispersants are added. Okay, now because of detergent, you may have some air bubble as well in the lubricant, so foam inhibitors are also added. So foam inhibitors basically help to reduce the air bubble formation. Other than this, there is another additive which is called viscosity index improver. Index improver. So viscosity index is something that we will study later. So again, viscosity index indicates how much the viscosity will change by changing the temperature. So viscosity index improver is also added. These are all some polymeric materials so that the viscosity will not change so much. There is one more thing which is called pore point depressant. So pore point is basically the temperature at which the liquid shows its flowing property. It flows. Okay. So pore point depressant is added for working in cold environment, because in cold environment the lubricant will freeze and therefore the lubricant will not work, at least in the beginning when you start the machine. So having lower pore point will help so that the lubricant remains in liquid state even at freezing temperatures, very, very low temperatures. So pore point depressants are added into the lubricant to help with this property. So now you can see that there are so many additives, and because of these additives actually the lubricant works so efficiently. The base lubricants, which are mineral oil or synthetic oil like silicon oil, or it can be PAO, polyalpha olefin. So these are the base oil materials. But in the base oil you add all these additives to make it suitable for your particular machine. So depending upon your situation of your the machine element and the environment, stress, velocity, temperature, you will have to decide about which additives should be used. Okay, and actually the lubrication engineers or lubrication companies, they all deal with these kind of things, and that is how they make lubricant for specific application. So nowadays lubricants are not like a general purpose that you can use for any application. Lubricants are meant for certain application, and because they have different levels of additives, different types of additives, in terms of toxicity also they have got different levels. Biodegradability also is another issue. So they will design the lubricant according to the application. So as a lubrication engineer, you will have to select these things, and based on that you have to select the lubricant. Okay, but if you are not in the lubrication business, but in the design also, you will have to deal with the lubrication engineer to make sure that you get the best lubrication. And as you know, no machine can run without lubrication. It will not run at all, or maybe it will run for only few cycles before wear will take place. So it is extremely important that we do this thing right. So now we will go more towards the friction reduction solution. So just now we went through the lubrication method, and we will talk more about lubrication, types of lubrication, lubrication mechanisms, and we have already talked about liquids, but there are also solid lubricants. Gases can also act as lubricant. Vapor or starved means marginal lubrication. We also talked about lubricants. So depending upon which lubrication method you are using, the lubricants you can select, but in the case of liquid lubricants, as I said, mineral oil, which are all hydrocarbons. Okay, so these are obtained from petroleum, and they are called paraffinic or naphthenic hydrocarbons. Paraffinic or naphthenic. Naphthenic hydrocarbons. They are all hydrocarbons. The mineral oils are all hydrocarbons because they are obtained from petroleum products. So during the processing, you get liquids of different natures, okay? Different boiling point and so on. So in some cases you will achieve this paraffinic or naphthenic hydrocarbons. So they are used as mineral oils. The synthetic oils are made by chemical reaction. So this can be silicon fluid, silicon oil, they are called silicon oil, or this can also be PAO, polyalpha olefin. So these are the lubricants. These are basically the base lubricants. We also use greases. So greases are basically oil inside a soft polymer. So soft polymer acts as the retainer, and lubricant oil will be inside the soft polymer. It's like a spongy mass, and the lubricant is soaked inside the spongy mass. So this is grease, and solid lubricants we will talk more little later. So bearing materials. So all these are different levels of solutions, different types of solutions, and under different situation we can use one or we can use more than one to help with our tribological system design. So we have to look towards the yield strength, the friction wear properties, the hardness and toughness. So any very well-known bearing material, you know? Can you give me name of one bearing material?
Babbitt alloy.
Babbitt alloys, okay. Anything else? In steel, which steel is used as a bearing material?
A stainless steel.
Stainless steel is not used. It can be used, but the bearing material which is used is AISI 52100. This is the bearing steel. So this is the grade of the bearing steel. Basically, this is a high carbon steel. Stainless steel is not high carbon, and in terms of strength and toughness, this may have a better strength and toughness. So this one has got carbon in the range of 0.98 to 1.1. This is carbon, and it also has got chromium. Chromium is in the range of 1.3 to 1.6. Another important thing about this, of course, it has got manganese and silicon, but another important thing is about sulfur. Sulfur is less than 0.025, and phosphorus. So these elements, sulfur and phosphorus, make the steel dirty. What we mean by dirty is basically because of this sulfur and phosphorus, you will have some impurities inside the steel. And just now we were talking about how to increase the fatigue life of a bearing material. So it is important that these levels are below this. Otherwise, your bearing steel will fail by fatigue process. So chromium is added for toughness, to improve the toughness, and carbon is added for improve hardness as well as the yield strength. Okay, so this material is not for reducing friction on wear. This is more for taking the load, bearing the load, and having a good toughness so that fatigue life is very, very high. So this is extremely important bearing steel. Often you will get by this grade, but some countries may have some different name for it, which are very similar in composition. For example, in Japan, I find SUJ2 or maybe 1 also. This is in Japan. Similarly, in Germany, there is another grade which is their bearing steel. In India, we always use this AISI 52100. So this is a very, very important bearing steel, and we should always remember that. All the bearing components like bearing balls and the raceways are all made of this steel. This steel can be hardened because carbon percentage is high, therefore it is hardened by oil quenching. So by oil quenching you can harden this material. There is another type of bearing material which are more like polymeric. Okay. Well, in the metals we also use bronze as a bearing material. Okay, and then polymers. Among polymers we can use for example PEEK, polyether ketone, and also ultra high molecular weight polyethylene. So these two polymers are used in their pure form or sometimes in composite form, but many polymers are used in the form of composites, polymer composites. So I will talk later more on the polymer composites, how they are used for tribological purposes.
Excuse me, sir.
Yes.
Sir, hair lubricating oil or material, apart from reducing friction and wear, they are bearing pressure, sir, and stresses as well.
The lubricant, yes, that is a good point. The lubricants are also supposed to have sustain lot of pressure. So pressure will be created because of the load. Okay, So for example, if I've got this kind of contact and this surface is moving in this direction with velocity v, let's say, so what will happen is the lubricant will be pulled inside. So this we will talk in the hydrodynamic lubrication. So this lubricant will be pulled inside and therefore it will be under extreme pressure here. So this pressure is important to carry the load, because whatever load you apply, there has to be a reaction force here to balance it, to keep in this situation.
We use bearing to bear this load.
Yes, but ultimately you have got liquid lubricant in between the two surfaces, right? So this liquid lubricant will be subjected to that pressure. So we want to avoid solid to solid contact, right?
Yes.
In all metallic contacts, whenever you have got metallic surfaces, you want to avoid this solid to solid contact. So there has to be a lubricant here. Without this lubricant you cannot work, and because there is a high load, so there will be a lot of pressure here. So these lubricants are supposed to carry a lot of pressure as well.
That's the reason we concerned about yield strength and toughness of that lubricating.
For the lubricants, there is no yield strength. It is more like a viscosity, which is more important.
So in bearing materials, you wrote yield strength, toughness.
Yes. Yeah, for the bearing material we need to have high strength because they will be subjected to very high load. Okay, and also we were talking about the contact stress. Even with lubricant, even in a lubricated situation, because the pressure is very high, there will be subsurface stress, shearing, and this shearing will make the material fail. So therefore the solid materials that we are using has to be very high yield strength, high hardness, and very good toughness to avoid fatigue wear. So fatigue wear will take place if we, for example, if I use let's say normal medium carbon steel as a bearing material, it will fail very soon because of fatigue wear, because of delamination and so on. So to start with, we must have the bearing materials very hard in the case of when we are using steel or ferrous material. But then when we are using polymers, then situation changes, because here we are not using lubricant. Here these solids themselves provide lubrication. Okay? So situation can be different. But just talking about metals, because of the high stress, subsurface stress, fatigue, we have to have a material which is suitable for this application. And in fact, if you see the history of this steel was developed I think around 1940s or in that time, but it took many years. It was not so soon. It took many years to develop this steel, and now we use this steel so much because of its good properties. Of course, there are some other better bearing materials as well. There is another grade which is better than this for high-end application, but this is more for general bearing application. Is that okay for your answer?
Yes.
Okay. Okay, so today we will stop here. Okay, I wanted to show you some samples. So here I've got two liquids in two beakers, right?
Yes, sir.
Can you tell me what are these? What could be this?
Sir, engine oil.
Okay. In my right hand I have got engine oil, and on my left hand, well, this is also engine oil, but yeah, but it is degraded form of engine oil.
Yeah.
So this is the oil you see in the workshops where they do the oil change. right? So this is a new oil, new engine oil for car, and this is the oil which has been used for something like 3 months in a normal application. Okay, so within 3 months you can see how the color has changed. Why? What happened? Why the color has changed?
Impurities present in this oil.
What kind of impurities?
Wear debris and
Yes.
and sir,
And
due to the high temperature, sir, there is a degradation in
degradation of the polymer, the oil here, and wear debris. So if you do the debris analysis, you will find that lot of metallic particles here. So where is it coming from?
between the contacting surface.
Yeah, so obviously it is coming from the engine parts, right? So that means the engine of the car is slowly wearing out, even though we are using good lubrication. So despite our effort to provide good lubrication, the wear is taking place still. Okay. So that's the reason why we have to be so careful about lubrication. We have to always change the oil, make it again fresh oil, and make sure no vibration takes place. Okay. So, and another thing you will notice is this oil, this degraded oil, doesn't settle down. So I was talking about detergent and detergents, right? Dispersant, detergent and dispersant. So because of the detergent and dispersant, this oil is always in this form, no matter how long I keep it in stable form. So in terms of viscosity, it has got almost similar viscosity. You see, I'm trying to shake. So in fact, this has got higher viscosity.
Yes.
This degraded oil has got higher viscosity, which is good for lubrication. But still, we need to change it because it doesn't have those additives that this oil has. Okay, so viscosity doesn't go down, but its quality is not good. Okay, so because of the detergent and dispersant, the particles are all dispersed inside. They don't settle down, and therefore they don't form any kinds of deposits. Therefore they do not form any kind of deposit in the engine. So they keep the engine still good, but what is important is we should change the oil. So this is very, very important, the lubrication part. So it is not only lubrication. The tribology, as you are learning from the very, very basic things, it includes many things: materials, lubrication, calculation of forces, velocities, temperature, understanding of the temperature, understanding the environment. So all put together makes a good tribological systems.